Any chance?
I'm back, yeah.
Yeah. Hi, everybody. Thanks for joining in today. As I mentioned, or perhaps as you saw in your email, what this is a part of the Neuro-Symbolic interest group on at the Alan Turing Institute, and we're excited to start on this virtual series. So I don't know if you've been following up, but we did a workshop at AMAS 2 weeks ago, which was really good. It was a filled room, lots of participants, and there was a panel discussion at the end. And what we're trying to do right now is to get a few people on board on doing these virtual talks. We'll record these videos. So if you have any issues on being recorded, feel free to write a chat privately to either Najesh, Najesh, if you can just wave your hand, Najesh or me, and we'll just read out the questions. So that's what we'll do. And for our inaugural talk, we're really excited to have somebody local. So it's my pleasure to introduce Ram. If you haven't seen Ram's work, you're missing out. So Ram's been doing a lot of work on a range of topics. I think confidently say he's potentially covered most areas of AI and planning, from reinforcement learning to Bayesian reasoning to program synthesis. And you might also know that for the last few years he was involved, I guess, as a scientific advisor, right, Ram, at FiveAI, which then got bought out by Bosch. So what we'll do is we started 5 minutes late to give people an opportunity to join. So if you're okay with this, Ram, we'll have you talk for another 45 minutes or 50 minutes as you wish, and then we can leave 10 minutes for questions. And depending on how the questions pile up and as the series picks up, we might then have a kind of panel session at some point as well. But for now, we'll have a Ram chat. And again, thanks everybody for joining in. Please take it away, Ram.
All right. Firstly, thanks to Vaishak for organizing this, and it's a pleasure to see all of you. So my intention today is to sort of tell you a story that's developed over several years and many papers. So there'll be places when I'm kind of going a little bit at a higher level over the detail. If you want any of that detail, feel free to ask, feel free to interrupt, and we can have a discussion. So what I want to tell you about is sort of a journey in terms of thinking about robot learning and thinking about situations in which that has been difficult for a variety of reasons that I'll tell you about, and how the difficulties have been mapped to questions about layers of representation and how we have needed combinations between learning, reasoning, and thinking through what I think is at the heart of what people mean when they say neuro-symbolic methods. I don't consider myself a neuro-symbolic AI researcher in that I don't come at it from the methods point of view. I come at it from the applications, and then the methods emerge in the process of solving that application. So let me start by giving you a few different examples to motivate the problem. So here's one example. And this is a large project that I was involved in with many different co-investigators from across Edinburgh and other universities. The premise of this, for the purposes of today's talk, all you need to know is that these are robots operating in fairly complex environments where the environment is very hard to characterize ahead of time. And there are a lot of subtleties about how people might want the robot to operate in these situations. And so a big undertaking when creating such systems is to come up with good ways in which the action of the robot can be interfaced with the desires of a human operator, and then sharing that situational understanding and coming up with ways in which you can say what the robot must do and diagnose that it is actually doing that and nothing else. Here's a slightly more restricted version of a similar use case, where you have the robot assisting a human user. So in this case, this is a video from a few years ago. This is Svetlin, who was my PhD student at the time, who's trying to perform an assembly task in this lab environment. And this Baxter robot is intended to help him. From an AI point of view, the question here is one of firstly, intention understanding. What is the person trying to do? Intention understanding in the context of a plan, because this person is going through a planned sequence of many different operations, and then actually acting in order to help. Now, if you're paying attention to some of the text that flashes up every now and then, all the text in red or pink, as the case may be for your display, is annotations by us. But if the robot were vocalizing for itself what it thinks it's doing, these are the kinds of things that would make sense of the robot's actions. So the robot is saying things like, I think he's doing this task, so I should hand him this. So if you ask yourself what kind of representations you need that span the spectrum from the low level of actual motor control and sensory motor control all the way up to, I think he needs a hand with this, so let me do that. That is, I would say, an interesting challenge for hybrid AI methods and neuro-symbolic AI methods. So this question of representations then gets looked at from many different perspectives. In AI, I mean, the question of what is a good representation goes back to the very heart of, 50, 60 years ago when people started thinking about AI, and nobody's ever stopped talking about it. But often it's looked at just from the point of view of efficiency of learning or efficiency of policy calculations. Whereas I'm trying to focus attention a little bit more on systems and their use in a human-centered context. So when looked at from that perspective, you sometimes find people really thinking hard about what is a representation for. Here's one example of a very nice paper by Cynthia Rudin, who makes the observation that if you're in high-stakes decision-making, then it's kind of pointless to use an opaque and so-called black box architectures and then try to figure out what it's doing. It might be better to, in the first instance, create models that have the structure that you want. And I take that last point, and then in some sense, the rest of my talk is going to be about how do you understand that structure and put them into the methods that we are interested in for robot learning. So let me give you, continuing this sequence of examples to motivate my problem, let me try to make things a little bit more concrete. Here's a typical example of the kind of scenario that an autonomous robot, in this case, a self-driving car, faces. For those of you who drive, this is a day-to-day, very familiar scenario, but it's fairly complex from a decision-making point of view. If you ask the question, should I enter the roundabout or not? Because you have to not only perceive where people are, but you have to perceive their future intention. And then you have to act in a sensible way with respect to this. So if you just looked at this image and said, this is a perception problem, or perhaps a video prediction problem or something like that, there are numerous methods for this. There's literally a zoo of neural networks that you can just take out of the literature as is. And you could say, I can apply them, I can score them in terms of accuracy, I can do performance evaluation. But then if you think about the decisions that you want to make with respect to this, maybe they'll be insufficient as a representation. Whereas here's an alternate way of trying to pose a problem like this, where what you're trying to do is to ask, what is car number 2 doing right now if you see that they've begun to make an action to cut into your lane where you're the blue car. A Bayesian way of thinking about it would be to say that there might be a hypothesis space, which is a set of goals. The goals could be that maybe this car wants to turn right, maybe this car wants to go straight. And given that kind of a hypothesis space, you can ask the question, what would an optimal planner do if that were the goal? So you're not just doing video prediction in the sense of what is it 5 frames from now. You're trying to ask in a reasonably long-term horizon, if this person were trying to go to goal 2, what might be an optimal plan? And you would see that there's a trajectory that that's implied by that kind of an optimal plan. And then you can do Bayesian reasoning with respect to that and ask, if these were all the possible trajectories for sensible ways of acting in the world, which of them is the best fit? And could that be a representation that I can use? That's a long enough representation that I can make forward-looking plans for my own vehicle with respect to. Here's an example of that kind of reasoning on a real scene viewed from a CCTV footage. And so what you see is that car in a box for whom we are making predictions, and you see an annotation on top of that box, which shows you a number of different possible maneuvers. and the probability of those maneuvers as that probability changes. And that's the kind of representation with which you're acting. Now, you could criticize any particular specific choice about how vision is done or how a prediction is done in this case. That's not important for the purposes of my current talk. What's important is for us to understand this notion of what kind of purposes we are using such models for, and what are the representational choices we are making. And so to conclude that sequence about my motivating examples, a lot of what I'm going to speak about today was done in the context of a Turing Institute funded project, where we were trying to collaborate with medics, and we were trying to think about ways in which you could apply autonomy in a surgical assistance setting, whether it's for diagnostics or kind of assistive operations in an operating theater setting, which from machine learning point of view really breaks down into, if you observe people's activities in the ways that I've been showing you in all of my examples, can you from that extract some kind of a high-level description of what is the activity that's being demonstrated to you in the sense of teaching? And then from that high-level specification, can you come up with guaranteed control synthesis? So this is why you want representations to have certain structure, because you want to reason about that structure. You want to make predictions that are not just in the sense of an immediate statistical prediction, but also in terms of some underlying properties that you might want these models to respect. So with that, let me jump in then to the various results I want to tell you about. So essentially, I'm saying that these are the kind of applications where we want to apply AI. And for us to be able to solve such applications, there are a variety of desiderata you want your models and methods to satisfy. So really what I'm going to do is to take you through results from a number of different papers that answer questions such as what I have on the slide. So let me start first from the question of what kind of compositional representations do we need in robotics, especially if you're trying to think about learning from demonstrations where human experts are giving you examples of performance of a task and you're trying to understand what that task is. So in robotics, people have understood for a while that a lot of what we try to do is compositional, in the sense that you can think about the activity of a robot in terms of local controllers and then sequencing or switching between these local controllers. For instance, in that picture that's shown for the robot, a local controller might be, I want to reach towards a green block. And then the overall task might be first visit the red block, then the green block, and then the blue block, and so on and so forth. Now, you could represent these in many different ways. You could, for instance, adopt a model-free policy synthesis approach. The argument is that if you do something that doesn't have any structure in your models and policies, you would find it hard to answer questions such as in that list there, what if I change the inspection order? What if I add a new object? What if I want to verify certain behavioral properties? It becomes harder unless you have this kind of composition structure built in. So to show you what this looks like when you're learning from examples, here's data of that robot being asked to perform that task from demonstration. And then the model learning pipeline would look something like what you see here, where you first extract what the primitives are, where the primitives are servo controllers towards objects. And then you learn on top of that what the programmatic structure might be. In this case, it would be a state machine style structure. And then once you've learned something at this level of description, it becomes possible for you to repurpose it, such as I want to turn the whole thing around by 90 degrees, or I want to, morph my coordinate frame in certain ways. All of this becomes possible because you have access to this high level representation. So this is what it actually looks like in a concrete task. So here the robot is performing the block stacking task, where the demonstration program has already been programmed such that the robot does this. The learning program looks at all of this data, and then it extracts as a vocabulary the list of primitive maneuvers that you see at the bottom of the screen. And then once you have a description of what the robot is doing in terms of this extracted vocabulary, you can easily see that it's quite easy for you to repurpose and write new programs, as it were, on top of this. And that then is the point here. The point is that somebody shows you one or two examples of what to do. You extract the vocabulary, you extract the structure, and then in a new situation or with a new specification, you repurpose that knowledge. And the point of having a structured representation is to enable that. Now, a question that always comes up when we build architectures like this is that, I mean, there's a lot of desire these days to say, can you have one integrated architecture that puts all of this together instead of having different pieces, one piece that extracts an object, another piece that learns a program, and so on. And so to make that point, we've also worked on methods that do integrate many of these elements. For instance, here's exactly the same task of learning a switched controller task, except the whole thing is done from pixel to controller in one integrated neural network, except that we're able to incorporate structure, in this case, a switching structure, which is done by the Gumbel softmax. And the switch is between different means and covariances for the controller, such that you can go from pixel to controller as many people would desire, but then you can have the structure that says, I'm doing this controller now, and then I'm going to do that, and then I'm going to switch to another one, and so on. And this is what it looks like. So the two visualizations show you what a switched architecture like the one in the previous slide actually gets you, where you can clearly see over time that it's switching between different modes of a controller and coming back, which is what that discrete continuous task is, as opposed to many other alternatives one could have adopted, such as a mixture model, which just kind of comes with an average controller that doesn't really do the task. So that's one example of thinking about a structured way of thinking about hybrid controllers and how one can perform learning from demonstration using a structured model that extracts the underlying design elements. Now, kind of continuing on that same spirit, we asked that the next question one could ask is, can there be more general forms to that structure, or are we stuck with this way of thinking about elementary controllers and switching between them? And so we asked the question, if we took a generic reinforcement learning pipeline, such as what you see in the screen, which is a description of a classical policy gradients approach, where you have a reinforcement learning framework, the policy is represented by a neural network, and you're acting on the environment. And then policy gradient says, can you take gradients of the cost function with respect to these policy parameters and improve? The question we are asking is, what if you had additional structure that you wanted to inject into this policy? So can you break it down such that you have a neural network component, which we call a perceptor here, which goes from pixels to an intermediate symbol set, and then a program, and I'll give you various examples of programs in the next few slides, which explicitly injects the structure of a solver. The solver could be a search procedure, it could be a controller, it could be various such things. And we're saying, I don't need to learn that from scratch. I know that structure, and I'm trying to ask, how do I combine that with my neural network? And how do I structure this whole thing in such a way that learning is efficient? And so as examples of this, here's the first example. This is a continuous controller task that people in reinforcement learning are very familiar with, which is to balance a pole on top of a cart without there being a direct actuation in terms of how to hold the pole up. And this is a nonlinear control problem because the dynamics of this system vary depending on where the state is. So you can't just have one linear model. Locally, you can have controllers such as a linear quadratic regulator, which is good in one region of that state space. And the question we are trying to ask is, if you knew that such a controller structure is good in some region of the state space, can you then build a pixel to controller kind of framework using a neural network paradigm, but then inject what you want for controller structure where you want it, in the same way that I've been saying in the previous slides? And if you do this, you get significant benefits to learning. You see that perceptor gradients, the approach that we are presenting, learns significantly faster than uninformed policy gradients. But this is just on a very simple task where we are beginning. But already you can see that the benefit you're getting of this kind of structuring is that you're doing a separation of concerns. There's one level, which is how do you extract some intermediate symbol set from high-dimensional rich raw data such that you can make sense of it. And the second level, which is how do you inject structure into the decision aspect of what you're trying to do. And so the argument here is that we do know quite a bit about the kinds of decision architectures we like. So it disentangles those concerns, and then it gives you programmatic regularization when you know something about the program. So to show the benefits of this, as we go up in complexity, here's a task in the Minecraft domain where the input is visual input in the form of what you see in those images there. And then the goal is that you want this agent to walk from one place to the other. The canonical description of what you want the agent to achieve does not need everything about vision. The canonical description can be described in terms of that grid world-like representation. And then we know that an algorithm like A* does very well. What we don't have is the mapping from the visual raw pixels to what should be the input set, which is what then Perceptor achieves in this case. And then you do this by closing the loop with a decoder such that the intermediate space is the latent space of an encoder-decoder architecture, and then the programmatic structure tells you what kind of a decision you want it to perform. And again, you see that doing this kind of structuring gives you learning benefits. And as I make the task more and more complicated by stacking multiple concerns, such as in this case, estimate the pose and then estimate the pose of an object with respect to that, and then do A* search, you see that the learning difference between informed and uninformed becomes significant. So here, if you look at the scale, we are talking about the difference between tens of trials versus thousands of trials. And that's what this kind of an architecture can actually get us. So as you can see, I'm kind of slowly working my way up in terms of different things that are hard about robotics problems, which are closed-loop decision-making problems. And we're looking at different ways in which we can inject structure. The next thing I'm going to take on would be, how do you provide specifications on top of which then the model can learn something? But before I move to the next section, I'd like to take a pause and ask, does anybody have any questions on things I've said so far? Okay, I'm not hearing anything, so I'm going to just continue along.
Yeah, I was just going to say, if people have questions, they can also put it in the window, but chat window, but either way is fine.
Yeah, okay. So continuing along then, the next thing that's interesting for us in robotics, kind of thinking about these notions of hierarchies and layers of representation, is to ask, how would you give complex specifications to a robot? So normally people think about it as, a robot has a simple task, such as pick up an object or something like that. But in reality, if you think about any task that you want an actual robot to do in what might be an actual home, there's a lot of structure around it. To give you an example, here's a very simple, seemingly simple task, which is, pick up that glass and scrub it, so that you can put it away and you can clean it. But if you interrogate what is the set of kind of specifications you have to give it, you have to first say, what is a green round scrubber? What is round? What is green? What is a scrubber? Then you have to say something about spatial relationships. You have to say place it inside that. Then you have to say something about the task, which is move up and down. Then you have to give modifiers of that task, such as press firmly and slowly. And all of these things have to come together for you to be able to meaningfully instruct a robot. And this is, again, one of the reasons why you want to think about how do you inject structure in these models, because if I just give a demonstration and say, here's the task, do it now, it'll be incredibly hard for a robot to just from a tabula rasa learn all of these concepts and immediately know what to do with them. And I'm arguing meaningful, realistic systems that can perform tasks at this level of complexity must be able to allow for different levels of representation so that you can talk to the robot at a high level, and then you can the robot can perform actions at a low level, and you can actually intermediate between these things. So in our lab, we've done quite a bit of work in this paradigm of learning from demonstration, where We initially collect data at very diverse, using very diverse modalities, ranging from teleoperation and visual observation to paired linguistic data, and sometimes specialized sensors such as eye tracking. And then the idea is that all of this is meant to study the question of how do you learn a rich representation. And then in reality, the robot has to perform the task by itself, not necessarily having access to many of these modalities. So how does one, observe an activity using all of these modalities and then structure a model to understand what the robot has just seen? One canonical paradigm in machine learning that's quite useful here, this is something I've already flagged up previously, is to take a bottleneck architecture such as a variational autoencoder, which is shown here, which is a neural network architecture which begins with the simple task of reconstructing an input to make it the same as an output by going through a bottleneck in the latent space, and then all of the structuring happens in the latent space. So I'll show you, for instance, for that big stack that we looked at, how you could structure the latent space to represent a hierarchical concept like that. The first thing you wanted to understand is a basic vocabulary, such as what is shape and what is color. And you can do this by giving it lots of examples and then forcing the latent space to have a structure, which is that, the size has to line up in one of the axes. It has to lie along the axis, and the smaller size has to be on one side of the latent space and larger has to be on the other side. Similarly, you can organize it for color. And these things can be now encoded as a geometrical constraint on the latent space, which then allows you to encode this idea that, I want you to understand the concept of color and understand the concept of shape. If you can start with this kind of a basis, then you can build on top of this, and then you can encode, by-object spatial relationships. You can encode action semantics, and that's when it gets interesting in terms of the kind of instructions you can give to the robot. So, for instance, here's an example of what I mean by object relationships. Here we mean things like what's behind what, what's above what, and so on. So you take these encoder-decoder architectures, and then you have a common space in between, and that common latent space is going to represent these concepts that we are interested in. And then once you can do that, you can chain them. So I can now, once I can teach front and then I can teach left, I can say to the front and left, or do this before that. And so this allows you to get at fairly complex controllers, such as what you see in this video, where the demonstrator wants to say, first do this thing with this cup, then do this other thing with this cup. And when you have done both of these things, your task is finished. If I gave uninterpreted video at this level, I have to literally give thousands and thousands of videos, which doesn't make sense in the scenarios we're talking about. Whereas by doing this kind of layered training that we are discussing, it becomes possible to structure the latent space such that the robot can actually, with relatively small number of trials, learn how to extract concepts like this. And so now it's able to respond to these kind of instructions that it's been given, and you see the robot learn the concept well enough that it's now performing that for itself autonomously. And then to quickly conclude that segment, you can now take the same idea of structuring the latent space, and you can do this in such a way that you can come up with conditional behavior generation in order to be specifying things such as do something more gently. So you take the same ideas that I've been giving for how you train a bottleneck layer, and then you expand that latent space to have action semantics such as quickly and partially. And then once you've trained it to have that in the latent space, you can now start giving a specification, do what I showed you before, except do it quickly. And then the robot would know how to do something like that. And here's an example of us being able to go from that kind of linguistic information about do something quickly or softly, and then translating it all the way down to the torques and the joint angles that it needs to change that task. So once we can do all of this, we can get at questions of safety that are becoming more and more important in robotics. So for instance, here's a nice example where the robot has been taught the concept of how to pick up a glass and empty its contents into another container. But then it makes mistakes lots of times, because if it hasn't been told one specific, common knowledge, kind of what would have been part of a frame in many of these older AI methods, which is that you need to be on top of the receiving container, otherwise you're just going to spill the contents. Then you might want to say explicitly, don't tip the cup until you're close to the bowl, but I don't want to give thousands of examples for each of these kind of specifications. I want to be able to give one single instruction the way I would give to a person, and I want the robot to modify on the basis of that. So to do that, we asked the question, how would you take post hoc modifications as essentially natural language in a logical form and inject that into the learning from demonstration pipeline. So the learning from demonstration pipeline, as I've been explaining, is that you want to start from image and end effector poses, which is being processed by a perception neural network, and then it goes into some kind of a parameterization of a controller. In this case, the controller is a dynamic movement primitive, which is a differential equation parameterization, the details of which are not important for what I'm speaking about now. What is important is to ask the question, if you have this kind of a neural network-based controller, and then you want to inject a logical specification or a logical form that says, don't tip the cup until you're close to the bowl, how does one do this? So the way we did it is that we first note that the logical form can be described in some kind of a formal description, in this case, a linear temporal logic, with operators that allow us to say useful things such as eventually and until. And then these logical constructs can be translated into a loss function. And there's many different ways of doing this, which have to do with descriptions of robustness or satisfaction of a logical formula. For the purposes of what we are interested in, this translation allows us to construct a loss function, which then gets augmented to the learning loss of behavior cloning or imitation learning, which is what we are doing in learning from demonstration. And then we can come up with paradigms in which we are explicitly probing for dissatisfaction of these formulae, and then taking those examples and adding that into the training set and essentially penalizing the neural network for not having learned that, such that the neural network very quickly learns to satisfy that instruction that you've given it. And this is what that gives you. This is the cup pour example, where an uninformed agent very often just drops the contents in random places, whereas the informed agent knows exactly what to do because it's been given that one single instruction will do this. And then you can have a number of different specifications, such as, when do you do something, how often do you do something, and so on. And then the final section I'd like to cover before we then have a discussion is building on this paradigm of the person being able to interact, interrogate, and give instructions. Can we actually have genuine dialogue? Can this whole process of the robot learning from the human expert be made into one of interactive task learning, which respects this whole hierarchy of what realistic tasks look like? So what we want to do is to have an online embodied conversation. And what that means is that learning for this robot must be incremental. It must be few short. And then it must respect the possibility that the hypothesis space of learning itself might keep expanding as you go on. And what would it mean to do this? And so this kind of challenges the existing paradigms of what makes many of these models successful. But it's also a very natural requirement for most human robot applications that I'm familiar with. So what we are looking at in this project, and this is current work, is to ask the question, if you understand semantics of the task, and this is something that we argue most people do understand at the level that they want to give instructions about what they want the robot to do, is it possible to come up with an architecture for robot learning in which the robot interleaves reasoning in terms of these formal semantics and find interaction mechanisms for injecting them with learning, which is what it needs for coping with very rich sensory inputs? So what we mean by reasoning with formal semantics is to be able to do things such as reference resolution or clarification, where you're trying to say, is this what you meant? Or can you show me what else looks like that so I know what you're looking for? And then by having these kinds of interrogation mechanisms, the robot is able to get the benefit with very few interactions of what would have otherwise been a very large data set to show all possible variations. So the kinds of things we would like to be able to target here would be, if somebody comes to you and says, brandy glasses have short stems, you would immediately, by kind of defeasible inference, infer a lot of implicatures from that, which linguistics people understand quite well, such as if you said this, you must mean that burgundy glasses do not have short stems, and so on and so forth, although this is not uttered by the person or necessarily shown to you with a lot of examples. And so what's going on here is the interleaving between the symbolic reasoning about what is implied and what is true with low-level learning, which is what the neural network is doing, and finding some way in which the dialogue is being used to improve the process of learning and to make interactive learning much more efficient. So what I've done is given you a high-level overview of several years of work and many papers involved in that, of an agenda which involves finding ways in which robot learning can be made more efficient for the purposes of the realistic uses that I argue robots will find themselves in, which is human-centered environments, the need to work closely with people, and to liaise with people in terms of the full complexity of the tasks. So not just kind of isolated tasks used as benchmarks, but full applications with complex specifications and so on. And so in order to do this, I'm arguing, and I think many people here would agree that you need to combine multiple paradigms for learning and reasoning, and in particular multiple representations and how you cope with them. And then doing this allows you to have more expressive mechanisms for the kinds of maneuvers that we are interested in, such as how do you actively explore the model, its limits and what its implications are? How do you allow people to offer corrections or representation change ideas such that the whole process of autonomy can be made much more performant? So with that, I'll stop. I'm happy to take questions. I'm open to discussion. So back to you, Vaishak.
Thanks very much, Ram, for a really inspiring talk. I think this is a lot of ground that was covered. I see, I think Matt had a question. Matt, if you want to feel free to speak up. Yeah,
I can ask you. Yeah, really interesting talk. Thanks very much. Yeah, so my question was just about just a practical question, really. So the variational autoencoder, where you sort of pre-train representations in that latent space, was really interesting. I just had a practical question. So how do you define the training paradigm such that you can force it to, say, look at size on a dimension and color on another dimension? And then secondly, after that, then what do you then do when you then train the full system? Do you freeze that? Because I guess it's like your vision system, or do you then use RL and maybe something like PPO or something so that it doesn't deviate too much from those representations? Just interested in getting a bit more color. It's probably in your paper.
No, these are very good questions. So firstly, to the question of how do we do this? So a variational autoencoder, I mean, the architecture in terms of how a neural network caricature diagram works is as you see that. It's a latent variable model. Normally, it's trained on the basis of a reconstruction loss and then a KL divergence term. We are adding terms to it, which then force it to have the properties that we want. So in this case, the third term that's been added to it penalizes for axis alignment. So essentially, you're trying to say that if I offer you, things with different shapes, I will penalize you if in the latent space they're not lined up in the way that I want. So yes, essentially giving it attributes of a loss function, which then makes it be like that. In the way that we did this sequence of work, it was indeed frozen at a lower level such that the higher level could learn on top. Now, as you know, machine learning moves fast, and already this is a few years old now. And if you use the latest and greatest kind of tricks of the trade, you could do more such that you could allow it to tweak. But this fundamental idea that you're coming up with loss functions that augment something about the properties of the latent space. That's a pretty reasonable one that's used by lots of people.
Thanks. Yeah.
Any other questions? Nijesh, I see a fairly long comment. I wasn't sure if you were trying to summarize or did you have a question that you wanted to ask? Either is fine.
So I was just thinking in terms of, I guess, as we move with robotics and like future directions with Neuro-Symbolic AI sort of connection, as we move into that, this concepts with solidity, occlusions, containment, sort of with objects and things like that, right? So as we get to that level, could we leverage Neuro-Symbolic AI in some ways to do something with, I guess, naive or intuitive physics in some ways? You know, for example, in the slide 12 and 27, we had these like conceptual and like pixel level information. Somehow we're trying to.
I mean, these ones?
Yep. So if we were to do like a bottom-up representational, thing with maybe intuitive physics inbuilt into the system, maybe we could reason on a higher level in terms of a common sense thing about doing these objects, right?
Absolutely.
So that sort of thing. I was, I guess, what is the future direction towards that? You know,
I think that is very much a good direction. So the reason, so you're completely spot on when you're saying the reason we want to have this hierarchy is precisely so that you can reason at the upper layers of this hierarchy. So AI has a lot of reasoning methods that are actually pretty good for what they are. The weakness historically has been that they've been brittle with respect to real inputs. And if you can solve that using methods that are good for that, which is typically neural network methods, then where reasoning happens, indeed, as you say, we want to have more expressive reasoning. Intuitive physics is one example of this, where we are saying that, so if you go with the Josh Tenenbaum kind of framing of this, the argument is that people have a small vocabulary of maneuvers, concepts, and tricks that they reuse across contexts and domains. And that's exactly what the robot should have. And it can only do this kind of a thing if you have a layered representation where it can kind of concisely apply it at the upper levels. But also the reason in the later part of my talk, when I was talking about dialogue and the reason you want to have formal semantics and so on, is exactly that kind of a thing where people might be able to say something quickly, such as it can't possibly be that objects come in and appear and disappear or something like that. Object constancy is a basic thing. Then you might be able to give corrections like that, but it'll be very, very hard to incorporate that in an unstructured model, and that's why you want structure.
So Ram, I was going to ask, and others feel free to ask if you have any questions. I was going to ask, since you mentioned Josh Tenenbaum, I was wondering from your side whether you see a kind of, how do I term it, a kind of synthesis of ideas from either a technical side or perhaps conceptually. So let's say you contrast one of your own papers on the one side and Josh Tenenbaum's work on the other. Do you look at the two papers and think, okay, they're in the same area, like Neuro-Symbolic AI, and leave it there? Or do you see like a deeper, structural thing? Because as you know, Neuro-Symbolic AI is not at the moment still lacking in foundations. Approaches are coming up, not quite exactly the same thing. So do you see some kind of deeper theory or framework emerging?
I see deep questions. Now, whether there's a framework is, how well can we answer that question? So let me give you one example of a question that's kind of very much on my mind, and it constitutes a big part of what I'm thinking about. So actually, it's well described by this example that I was giving you guys. So if you took prediction, and if you think about what is one doing, so it's actually, let's go back to this picture, right? So this is a very, very caricatured example of the real world, but it's a reasonable description. What we are arguing is that the process of making so there's no way to act in this world unless you have a prediction about other agents in this world. It's a necessity. And then predicting the other agent in the world is to somehow synthesize a simulated description of their future. So you're building a simulator and you're saying these are the things that two could do. And that's what I'm doing. Now, in Josh Tenenbaum's framing, he has a lot and very nice things written about, how simulation is at the heart of mental models and so on. But they do it as cognitive scientists in very, very stylized cognitive science style experiments. Whereas I want to do it in these kinds of environments. And of course, there's a lot of messiness to these environments that I'm operating in, for which reason cognitive science people wouldn't look at it. But at the core of it, the core question for me is always, in what sense is prediction a program synthesis question over, vocabulary that you're somehow inducing, right?
Yeah.
So I think everything that I'm working on has that flavor to it, where there are a very few small number of conceptual questions that are fairly foundational, and if we could have very good answers to them, they'll be very useful. And then it'll be up to us in the application areas like robotics to take them and run with it and kind of build very performant tools with it. But this core question of what is prediction really, or what is understanding really, they are pretty foundational.
Yeah, I mean, I guess to some extent, we can't expect to resolve completely, right? So it's a bit like trying to argue for Python versus Java, and you can go back and forth for years and still not resolve. And so perhaps there's a bit of that, but still, when you think about programming languages, you have certain abstractions and computational kind of structures that just come up. Right, recursion, etc. So it would be good, I think, at some point, if, as you say, there's a kind of fundamental questions and there's a way to think about them in a very structured way. But I suppose that's for the future, for some young person maybe in the audience to take up and run with. Any other questions from the audience? Yeah, go ahead. Anis, if I'm pronouncing that name correctly.
Yeah, it's correct. Thanks a lot for a very inspiring talk. I especially appreciate the focus on real-world robotic problems. I was curious to know your thoughts about, because you mentioned human-robot collaboration, and we see we're moving towards large language model robot collaboration. So any thoughts in this neuro-symbolic paradigm from you?
Yeah, I mean, this is a big question, right? So in fact, I mean, one of the things I'm often nervous about these days when I present, so this line of work that I presented about, giving instructions, if you look naively, the first question people ask is, doesn't an LLM solve this? One answer is no, because LLMs are not grounded. And I think everybody working in that area understand that. And the grounding is a huge problem. But LLMs also give you cool things, right? So if I were to ask the question such as, I have a cup sitting on a table on the edge, what might happen in the future? For all I haven't tried this, for all you know, you put this into ChatGPT and it says it might fall down. Now that's very useful from the point of view of future prediction. That's now a useful generator of hypotheses where you probe this many times and it says it could fall down, it could stay on top, it could slide back, it could do something. And this is now giving you a hypothesis space to then resolve using more fine methods doing other things. So I see scope for that in those ways. And I mean, I try not to be fundamentalist about any of these methods, especially because I start from the applications. So there's very nice possibilities about using generative AI as so if you go back to classical AI, generate and test was one of the paradigms. If generate can be done really performantly because of these new methods, why not? Then it allows you to do very cool things with that. The danger, of course, is to then go all the way in the same way that within robotics about 10 years ago, people got very excited about everything can be done model-free from the pixels. And then now everybody has gone back to saying, no, we need structure. So in the same way, if somebody comes and says LLMs will do everything, stop training anybody, that would be nonsensical in the same ways. But they have, I think, useful roles to play in pieces of such pipelines.
Thank you.
Ram, there's also a question from Katya in the chat. I don't know if you can see it or you have to.
I'm not looking at the chat, so if you wouldn't mind, just please ask.
Yeah, so Katya, I don't know if you want to speak up, but.
Yeah, I can briefly.
Yeah, go ahead.
Hi, Ram. Thanks for the great talk. I noticed that you mentioned generation of loss functions from logical properties.
Yeah.
My team has had a look into the problem, and for us, there is a huge chaos in the area. We see lots of different translations, and it's very difficult to choose one over the other. So my question was about your opinion about the state of theory concerning loss function generation from logical properties.
I agree with you. So I get the, firstly, we're not experts in that domain. So we've kind of adopted ideas that were originally initiated by others. I do get the impression that there are a lot of options. I mean, the one that stands out for me the most, is of course the fact that, so when I say, so when I gave you the example of, put the cup, first get on top of it and only then tilt and so on. There's no 100% guarantee of satisfaction because of the translations we're doing. There's a small possibility that the softening was a weakness, right? So these are all true, and we don't know of better ways to do it. And if anything, we are looking for people who are experts in this domain to say more about it.
Thank you. We're working on it.
Yeah.
Thanks, Katya. Any other questions? If not, Ram's available by email, although all of us get too much email. But what we'll do is, as I said, we'll do a recording. We'll stop the recording now and put up the recording on